Hi and hello everyone. Let us continue our discussion of continuous time Markov chains that we have seen in the previous lecture. Recall that what we have seen at that point of time, that we looked at this Kolmogorov forward and backward equations for the transition probabilities which are obtained as in this manner, which is in matrix notation. It is given in this form where this P, Q, everything is in matrix, which has solution of this. Okay. Now, if you are looking at the state probabilities, which is what would be the interest in our case, because we are looking at the not rather than the transition probabilities, we will be looking at the state probabilities only. So, this is what is our interest. So, this if we define PIT to be the probability of being in state I at time t, then if you call this as a vector of this entries Pi of t, then again this Pi of t can be characterized via the system of differential equations. It will be in general differential difference equation, which is also forms of forward and backward Kolmogorov equations as given in this form. This is very important that P dash of t is equal to P of t times Q is what is the forward Kolmogorov equations. Now, given Q and P naught, we can solve this, right, much like here. This is also something similar. Given P0 and the matrix Q, like you are able to get the solution to this in a much similar way. We can also obtain the solution for this particular thing. Okay, so this is the main system of equations which we need to solve in order to get the state probabilities, right? Because that's what of interest. Like in a Markov chain, after some time or at particular time t, what is the probability that you are finding it in particular state is what is of our interest. So, we have to solve effectively this system. Okay. Now, as an example, what we considered was a BD birth death process. So, in which the state transitions happens to the nearest neighbors, which means they either increase the system state by 1, which is what we call it as a birth, or decrease the system state by 1, which is called as a death, and the generator matrix would be of this form for states 0, 1, 2 and so on. Okay. So, which means that when it is in state 0, with a birth it can go to state 1, right. Now, I mean, if it is a population, depending upon the context, we have to interpret what we mean by this birth here. If it is a population, if there is 0 is the number of elements or the number of entities in this population, then with 0 elements or 0 species, that you will not be able to generate any new species, right. So, what does that, then it makes sense, it has to be looked at little carefully. So, in that case this would be mean that something like an immigration kind of thing. But in our case, it is in a queuing system. Birth corresponds to an arrival of a customer to the system. So, it increases by 1, system state increases by 1. So, there could be arrival to an empty system from outside, right. So, that is why in our case that does not make much of a problem, but if you are trying to apply this model elsewhere, then one has to make sense of what do we mean by birth and at time 0 what do you mean by this, because this lambda I is defined for I greater than or equal to 0, and death rate will have no problem because mu I will be for I greater than or equal to 1. There has to be at least one person or one entities if it is a population, or one customer if it is a queuing system, before we talk about its departure. Okay. So, that is why this mu I is for I greater than or equal to 1, lambda I is for I greater than or equal to 0. So, in other words, if I write the Qij's, so this is what would be this Qij's is what is the description here, right, and we will get this special structure which is a triangular structure, which is very special structure and it has lots of properties of this matrix can be used to obtain the solution, right. As we know, once we are giving Q, right, and P naught, we want to obtain this P. So, which means that this Q will, if we have some structure, then how one can get the solution for P of t. Given a possibility, we want to obtain using this Q, we want to obtain solution to this system of differential equations. Then we got it for all time t, what is the probability that you are finding the system at particular time t. That is what we would want to do, right. So, this in this particular case, because of the special structure, the transition rate diagram would be as given here, where 0, 1, 2, 3 are all the system state. The increase can happen at each state with the corresponding rate. Suppose if it is in state n, then lambda n is the birth rate. So, you will get this as lambda n, and if it is in n, the death rate is mu n. So, you will get this, okay, whether it is n is 1, 2, 3 and so on, accordingly you will get this. So, this system of differential equation, which is what is forward Kolmogorov equation for the system state probabilities, which is effectively this quantity, right, for this particular q will take this form, right. So, this is the most important system of equations in the analysis of birth death model. If you can obtain a solution to this, that is what ideally you would look for, then you can talk about the system or the process, the birth death process, or the which is a continuous time Markov chain, being in a particular state at a particular time, you can always get this probabilities, right. So, that is what it is. So, that is what it would mean, this system of equation solution to this is what you ideally look for. Now, whether it is always possible to obtain, and if so, like how complex is it, whether it makes sense that even you are looking for it, that solution is all the question that you ask with respect to the BDP. Many queuing systems where the customers arrive or depart the system one at a time can be represented as birth death process, because as you know, birth death process, the system change happens by at most one state, neighboring state, either it increase by 1 or decrease by 1. So, that would correspond to arrival or departure from the system one at a time. Okay. For example, MM1Q, where all lambda I is equal to lambda, mu I equal to mu, is what would be the Q that we will see later. Okay. So, how do we obtain this equation? Like again, you can recall the Poisson process case, where we obtained this from the basic principle. Here also you can consider it in the interval of length 0 to t plus delta t, and dividing it between t 0 to t and t to t plus delta t, you can obtain by the same process, you can obtain this set of equations, right. But which is what using this rates that you will get here, and that is what you will hear here. Otherwise also, like you can obtain it from this diagram, you can straight away write down this, where this would mean flow into the state. For example, if I look at the state 0, so this is the flow into the state and this is flow out of the state, right. And so, the difference is what would be the growth of this P0 of t, right. That is what interpretation here also that you will do it here. Okay. So, this is what one would ideally like to do, that to obtain P of t, whether it is a transition matrix or the state probabilities, if one is possible. But just like in DTMC case, our interest is what happens in the long run behavior of the continuous time Markov chain, right. That is what we are also interested here as well. So, basically what you are looking at, much like DTMC case or the Markov chain case, you are looking at Pij of t as t tends to infinity. This is transition probabilities as time tends to infinity, or Pi of t, the state probabilities as t tends to infinity, is what the quantities that is of interest for you, right. What you are looking at is that limiting probabilities, which how one can obtain. This, the whole idea is exactly similar to what you have done in discrete time. As in the case of discrete time Markov chain, or simply a Markov chain, for some nice CTMCs, we know what it means to say that it is a nice CTMC. We have seen it in DTMC, almost similar thing is what is going to happen in CTMC. A unique stationary distribution would exist, and that equals the limiting case. That is what ideally we would like to have. Okay. To do that, we shall assume that the technical assumption that each of these lambda i's are strictly greater than 0. So, lambda I equal to 0 case, which is basically the absorbing case, is what we are excluding here by this technical assumption. Already you know that this is bounded, we have made it. Now, we want to know assume that this is also strictly greater than 0. Now, a CTMC is irreducible, transient, recurrent, whether it is null recurrent or positive recurrent, if the defining Markov chain is. So, whatever the DTMC that we are using to define the CTMC, whatever the properties that DTMC has, it carries over to the CTMC as well. If the DTMC is irreducible, the CTMC would also be irreducible. Whatever the Markov chain or simply Markov chain or discrete time Markov chain, if that is positive recurrent, then the corresponding CTMC is also positive recurrent and so on, right. Now, let this Yt be a CTMC with transition matrix P of t and the state space 0, 1, 2, then a probability distribution P on S, which is just this vector, right, is said to be a stationary distribution for Yt if it satisfies this equation, right. It is a distribution. So, already like we assume that the sum to be equal to 1, this is P equal to P times this transition matrix P of t for all t greater than or equal to 0. So, in case of discrete also, like you have a something similar things that you know. Here we want to require that this is for all t greater than or equal to 0, this should be true, and a P which is of this form is what will be called as the stationary distribution. Similarly, the probability distribution P, which is a vector, is called the limiting distribution of the CTMC if Pj is basically given to be limit t tends to infinity of probability of Yt being in J given that y at 0 is I. And if you recall, this quantity is basically what you have, this is P I J of t. So, it is essentially much like in the discrete time case. Here also you have a similar situation where you are looking at these transition probabilities in the limit as t to infinity, the limit exists and is independent of I, right. So, that is meaning that if I look at this P of t matrix, this P of t matrix as t tends to infinity, the rows becoming identical is what then will be independent of I and the limit exists. So, this follows a distribution, right. If this is the limit Pj and they sum to 1, then you have a limiting distribution, right. Limiting probabilities may exist, but the limiting distribution may not, much like the DTMC case, that is also same thing here. Okay. So, this is what ideally one would want. We basically want to know the long term behavior, which is Pj, but again the interpretation for Pj is like in Markov chain case, what is the probability that you would see the system being in state j a long time from now, whereas stationary distribution meaning that the long time proportion of time that you would find the system to be in a particular state, right. The same interpretation which we had it for Markov chain. Now, for example, if you look at the two state continuous time Markov chain which we have seen, okay. So, this is what you had it, right, the two state Markov chain case, which is the P of t we obtained to be this, right, we already obtained it in the previous lecture. So, this is what is my P of t. Now, with the P0, P1, the equations, this equation gives this as the stationary distribution, and we also observed already like limit of t tends to infinity of this P of t will be half, 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 half is the matrix of all halves. So, that means that is the stationary distribution and that is the limiting distribution as well. Now, here this is a nice chain with a unique stationary distribution that equals the limiting distribution, right. But here one thing which you will notice with respect to the discrete time Markov chain and continuous time Markov chain, here what is that in discrete time Markov chain, what is the defining Markov chain here? Defining Markov chain here is 0 1 1 0, right, that is what is the defining Markov chain. If I go back and if I write, look at that, okay, look at here, this is the defining Markov chain that we had it for the two state Markov CTMC case, and this was your P of t that we have obtained earlier, right. So, this, and in DTMC case, what was the stationary distribution, what was the limiting distribution idea? If you recall, for this P, right, we said that there is no limiting distribution, right, in the way that we have defined, right, because it is never becoming independent of the initial state, but it has a stationary distribution which was half-half. It has a stationary distribution, but it was not having any limiting distribution. But here the corresponding continuous time Markov chain has a limiting distribution which is same as the stationary distribution. So, what was the difference? What was the property that we had it there which was not guaranteeing us in the case of discrete time Markov chain the existence of limiting distribution was the periodicity property, that aperiodicity property. But here in continuous time the periodicity does not play a role, and that is why this happens, and this is now becomes a nice chain. When in the continuous time case this becomes a nice chain with a unique stationary distribution that equals the limiting distribution. So, in theory if you want to find such a distribution, right, such a distribution which is stationary distribution as well as limiting distribution, right, what we have to do? We have to solve this equation, right, by solving this or finding this, which means we have to find this kind of distribution, this p of t, and then take its t tends to infinity to get that distribution, or we have to solve this for every t greater or equal to 0, a solution we have to obtain, right. Now, in practice, remember in both these cases we need what is p of t, here also p of t and take its limit, here also p of t, and you are solving this system. So, but getting this p of t is not such an easy task. So, it is very difficult. Even in very simple cases this will be a very complex process, and you will find it very difficult to get this p of t even in very simple case. We will exhibit one later, but for the time being you take it for granted that even in a very simple case this is not easy to find this p of t. Hence, direct determination of this such a steady state solution which is given by the stationary distribution or a limiting distribution is not a very simple job. Direct determination means like you obtain p of t, and by taking its limit or by using this system you are obtaining the stationary distribution, which is what is the limiting distribution, which is what you ideally want to have. So, we need to find an alternative way to do that, because obtaining this itself is a very difficult job. Once you obtain this, then by taking its limit or by solving this you can think of obtaining the solution, which is what ideally you look for, which will give us the interpretation that a long time from now where you will find the system or the process or the Markov chain, or what is the long term proportion of the Markov chain into this case. Okay. But since this itself is difficult, now the question of taking its limit after getting this PT is also not a very simple job. So, we need to find alternative ways. Is there any alternative way to obtain this particular thing? And that is what this theorem gives us. What this says is the following: for a continuous time Markov chain, if the embedded DTMC is irreducible and positive recurrent, then if the embedded Markov chain is irreducible and positive recurrent, then this CTMC is also irreducible and positive recurrent. That is what we mean. Then there is a unique stationary distribution given by the solution to the stationary equation, which is what is given here, which is basically the 0 vector is equal to p times this matrix Q, the rate matrix Q, and summation pi equal to 1 is what. This is what now the stationary equations in the case of continuous time Markov chain. Remember, in case of discrete time Markov chain, we had it as pi equal to pi p. The p was the transition probability matrix, such that summation pi equal to 1 was the stationary equations in the case of DTMC or simply Markov chain. But for the continuous time Markov chain, this is the stationary equation, right, 0 equal to pq. Now, further, under our assumption that the mean holding times in all states are all bounded, which means lambda I is strictly greater than 0 for each I, the chain has a limiting distribution which is equal to the stationary distribution. So, if that is the case, you do not have an absorbing chain. That is what it would effectively mean, that is what it would mean an irreducible thing, right. So, already like we are imposing this condition. So, in that case the chain has a limiting distribution that equals the stationary distribution. So, now if you want to get that distribution, which is we call either stationary distribution or limiting distribution, then you don't need to look for solving this after getting P of t or taking the limit reach infinity after getting this P of t. What you can do, you can simply solve this. Okay. Now you know what is Q, there is no t dependency here, it is a single matrix. You solve this equation with this, and if the chain has this property, irreducible and positive recurrence, and mean holding times are all bounded, which means that it stays only a finite amount of time in a particular state and it makes move to the other state. That is what it would mean, right? Then this is what you are looking for as the quantity of interest for you to know about the long term behavior of this continuous time Markov chain. Now you can see that a continuous time Markov chain is said to be regular, we use the word regular, if it satisfies the conditions given in the above theorem, which is irreducible, positive recurrent and the mean holding times are bounded. And for a regular Markov chain, this holds, right? The transition probabilities, not just the state probabilities, the transition probabilities, if I take its t tends to infinity, they becomes Pj and independent of I, and this is what the state probabilities, which you can obtain it from this equation. So this is also true, right, for a regular Markov chain, which is regular means you are irreducible positive recurrence here. Now as you can observe, compared to DTMC, the aperiodicity, the period is equal to 1 is not required for the limiting distribution to exist in the continuous time Markov chain, as the time between transitions vary continuously. Even if the embedded Markov chain is periodic, the continuous transition times wash out any periodicity that may come from the embedded process. Like we have seen already an example, right? This is the example that of that nature, which has a period 2, but in discrete time, so it does not have a limiting distribution, but in continuous time it has a limiting distribution. So the periodicity is not required in the case of, because there is nothing like a period for a continuous time, because time is continuous, right. So that periodicity is getting washed out. So there is no periodicity concept as such for continuous time Markov chain, you can take it in that way, right. So we are not looking at that. So basically that is why irreducibility and positive recurrence is what is your, in the discrete time case, the stationary equations were different, but solution of that was possible if this was the case. And in case of aperiodic Markov chain, we said that the limiting distribution exists, then it equals the stationary distribution. But here we do not need that aperiodicity condition, is what is the difference that you would see with respect to the ergodic theorem for the continuous time Markov chain, which is what this result is all about, right, much like the similar case for the discrete time Markov chain case. So if you are looking for long term behavior, limiting distribution or stationary distribution, they will be then in under such situation irreducible and positive recurrence and this boundedness. So they will be given by the solution of these equations, which is an alternative way and which is a very simple one to do now. Just like in the discrete time case, you have to find discrete time Markov chain case, you have to find p to the power n to get the Einstein transition probabilities and then let n tend to infinity. Instead of that, you solved it through pi equal to pi p and then you obtain that same quantity. Here this is 0 equal to pq is what is the equation that you need to solve to get the distribution, right. If you get this pi's, then if it forms a distribution, then that is what the stationary distribution and that is what the limiting distribution in this under the conditions given in this ergodic theorem, and that is what you want to look at it. Then this piece, whatever you have obtained as a solution to this set of equations, is what will give you the probabilities of finding the continuous time Markov chain to be in a particular state a long time from now. The interpretation is by a limiting distribution, or the long run fraction of time you find the process in a particular state. This is basically from the stationary distribution point of view, right. So this you can have these both the interpretations for this piece that we have here. Now this equation, if I look at it, because now I need to worry about only solving about this set of equations, because this is what will give me the equilibrium behavior or the steady state behavior or the stationary behavior or the limiting behavior of the continuous time Markov chain. All these words are used interchangeably in different contexts, you be aware about that. Okay. So, the steady state solution or the equilibrium solution is given by this set of equations. Now, what is this? If you rewrite this in the expanded form, this is by taking out only the jth term alone and the remaining one in this sum, this is what it is, right. Now, this one Qjj is effectively this one, right, minus times Qji for I not equal to j is what is the case. So, this is what it means. Now, what is this quantity if you look at it? Pi Qij is the rate of transitions from I to j or stochastic flow from I to j in equilibrium. So, in equilibrium only, like this is what is the equilibrium flow balance equation, this is what it is. So, that how does it gets interpreted is what we are looking at it now. So, Pi is basically the probability of finding the system or the process or the chain in state I, and Qij is the rate at which it is moving from I to j. So, the total, the product is the rate of transitions from I to j, because you are finding it in I and then it moving from I to j. So, that product will give you the rate of transition from I to j or the stochastic flow from I to j. Now, summing over I, right, will give you the overall rate of transitions into state j. So, from whatever I, the I could be anything other than this j. So, that is what this would mean, right. So, I not equal to j, which means from other than state j, from any other state, the transitions into state j is what would be the left hand side. So, the right hand side is basically you are finding it is the state is in j and j to I, it is moving for I not equal to j. It means this is the rate of transitions out of state I. So, Pj Qji is the rate of transition from j to I, and if you sum over all I not equal to j, then it will be give you the total rate of transitions out of state j, the same interpretation that you have. So, this is set of equations, then it would means that the rate of transitions out of a state equals the rate of transitions into the state. That is what you expect in equilibrium to happen, or for steady state to hold, these two rates must be equal. So, this is what is the flow balance equation that you have. So, and hence these are all called the balance equations simply, or global balance equations. Now, for the case of Poisson process, is an example if you look at it. PQ equal to 0 gives this and this, right. So, this implies that Pi equal to 0 for all I and there is no stationary distribution. The reason also you will know whether it satisfies the ergodic theorem conditions. You can verify, check and see that why this is happening, that all Pi's are equal to 0, okay, and there is no stationary distribution here. Okay. So, this is what is the flow balance equation it would mean. So, you could see that in that particular case with the rate lambda, it is moving out from state I, it will move to state j or I plus 1 in that particular case, or from I minus 1 with the rate lambda, this will come to state I. So, that is what it happens here, the flow balance. And for the two state Markov chain, which is what this Q is here, this equation gives P naught equal to P1 and P naught plus P1 equal to 1, and that implies that P naught and P1 equal to half each is what this would give you. Now, let us come back to birth death process, the most important one that we are going to use next. Recall SETMC with transition rates I to I plus 1 is lambda I to I minus 1 is mu I, and for Ij for which is more than one state apart, they will all be equal to 0 and the Qia will be given by the usual process. Now, we will assume that lambda is strictly greater than 0 for all I greater than or equal to 0 and mu I is also strictly greater than 0 for all I greater than or equal to 1 and are finite, right. Then only all this whole chain will be irreducible, and you can now then talk about the further progress of finding solution to stationary equations. Okay. And since these rates are all strictly greater than 0, the boundedness condition is satisfied, and with again with strictly greater than 0 for all i's, ensure that all of these states are communicating with each other. So, that means that starting from 0 I can obtain 3, like I can go to 1, I can go to 2, I can go to 3. From 3 I can go to 0, right. So, I can go here, I can go here, again I can go here, I can come here and I can go here. So, there is a possibility that I can reach 0. So, they communicate in a way, right. So, all this becomes an irreducible Markov chain or irreducible BDP. Now, again the balance equation for this would be this, right. You look at state 0, the rate of flow out of state 0 is, it is in state 0 and with rate lambda naught it is moving out. So, lambda naught P naught would be the rate of flow out of state I. Now, what is the rate of flow into state I? It is at 0 here. It can come to state 0 only from state 1. So, P 1 times mu 1 is what would be the rate of flow into state 0. This is the boundary state. So, it will have this separate equation. Now, suppose if you take any generic equations, yes, let us take the case of 2 here. Now, what is the rate of flow out of state? So, the rate of flow out of state is either it can go move to 3 with rate lambda 2 or with 1 with rate mu 2. So, the rate of flow out of state 2 is basically lambda 2 plus mu 2 times P 2, right. That is what you will get on the left hand side here, which is the rate of flow out of state 2. And what is the rate of flow into state 2? That it can be in state 1 and with lambda 1 it can come to state 2, or it can be in state 3 and with rate mu 3 it can come to state 2. So, lambda 1 P 1 plus mu 3 P 3 is what you will get for I is equal to 2 here, right. That is the rate of flow into state I, rate of flow out of state I, and in equilibrium this must be equal. So, this is what is the flow balance equation. Now, this one you can also obtain, you have the Q already, right, you have the Q already, and then you can look PQ equal to 0, you will give you this, or from this diagram you can immediately write it down what is the flow balance equations, right, which must be satisfied in equilibrium. Now, this BDP is irreducible under our assumptions. If it is also positive recurrent, then we will have a unique solution to the above equation, and it is called as stationary distribution or limiting distribution or equilibrium distribution or steady state distribution for the birth death process. That is what you would call the solution to this, right. Again you look at the theorem, how we are using it, recall the theorem. Irreducible positive recurrent implies there is a unique solution to this set of equations. Now, we are ensured irreducibility, we have ensured the boundedness, we do not know it is positive recurrent or not, or under what condition this will be positive recurrent. So, we look at now the solution to this set of equations. Now, when under the what condition the solution, this system has a unique solution, and that is the condition for positive recurrent. That is how we will interpret. So, if it is positive recurrent, then we will have a unique solution to the above equations, and it is then called a stationary distribution or limiting distribution, because we know all of them are, these two things is what is the main quantities, they are one and the same, and whenever one and the same, the additional words, terminologies that is used to describe is also called equilibrium distribution or steady state distribution for the BDPs. Okay. Now, we now address this question of existence of the steady state probability distribution for this condition. Now, for which what we do is we define two sums say S1, which is summation k is equal to 0 to infinity of product of I is equal to 0 to k minus 1 lambda I by mu I plus 1. So, if I expand this product, what I will get in the numerator, it is lambda naught, lambda 1 and so on, lambda k minus 1 divided by mu 1, mu 2 up to mu k is what this product would be, and the sum over k is equal to 0 to infinity. This is the sum S1, and this is S2 is another sum which you define it to be this particular case. Now, it can be shown, it can be proved that the BDP is positive recurrent if and only if S1 is finite and S2 is infinity, because this sum is finite and this sum is infinite. If that is the case, then you have the BDP is positive recurrent, and this will be null recurrent if and only if S1 is infinite and S2 is also infinite, then in this case this will be null recurrent, and this will be transient if S1 is infinite and S2 is finite, right. So, if I want only the recurrence or transience of this, then I can take only through S2, right, because if S2 is finite then it is transient, if S2 is infinite it is recurrent. Now, within this recurrence, if I want the positive and null recurrence to be separated, then I have to look at essentially this S1, which is what is the most crucial one here, and if S1 is also infinite then it is null recurrent, and if S1 is finite then it is positive recurrent. So, but mainly our interest is whether the chain is positive recurrent or not. If that is the scenario, right, I can look at only S2, S1 will be finite, S2 is infinite, obviously you have to verify, but we will be mostly concerned, or will be without saying explicitly, we will be concerned with S1, if S1 being finite or not. If S1 is infinite, then I know that it could be one of these cases, right, S2, but S2 needs to be checked, but it will satisfy anyway most of the case, so we will not worry too much on this part. So, this becomes the major or the main one which will contribute to our positive recurrence of this chain. So, it is the case 1 which is the BDP is positive recurrent, that gives rise to equilibrium properties, and this is of interest to our studies, where both S1 and S2 though is needed. We will not say explicitly about S2, which you can verify by yourself, but it will be in terms of S1 we will talk. And note that this condition would be satisfied if whenever the sequence, this ratio lambda n by mu n, it remains below unity from some point n onwards, right. After some certain point of time, time here this n, then if it remains below unity, then this will be the case, that one can see easily by looking at this rate. So, ratio of rates is what will give you an idea. Now, an irreducible BDP on a finite state space. So, currently the BDP is in general is on a countable state space, but whenever it is in the finite state space, this is said to be simply a finite state BDP or simply finite BDP. I mean, sometimes very shortly we might use the word finite BDP rather than finite state BDP, but it means the same. And in such a case, if the thing is irreducible, right, this is always irreducibility we have assumed, this is always a positive recurrent. So, we do not need any conditions there whenever this finite state space models that you are considering with respect to this BDPs, right. So, this is what is the BDP theory, and then we will come back to this BDP once more when we start the next lectures, which is on the basic queuing models. But this is what we may have, we may not have everything, but this is what we will have. This is what is called the global balance equations, and a solution to the global balance equation is what you are entailing. So, this can also be obtained from that the stationary equation 0 equal to PQ equal to 0, like this also gives you this flow balance equations. Okay. So, we will stop here, and about our discussion on this continuous time Markov chain, what we will do next lecture is we will start the discussion of our basic queuing models, which will be based on this BDP. So, again we will revisit BDP once more when we start the queuing models. Okay. So, this is all our basically our idea is that what is a continuous time Markov chain, what is required to describe a continuous time Markov chain, and how you will obtain this long term behavior. So, the long term behavior, equilibrium behavior is what we are looking at it for most of the queuing models that we will do, but we will also highlight at one point of time for the simplest of the model what is the transient solution, which is basically obtaining P of t, the state probabilities at time t explicitly, and you can see then the complexity of obtaining that P of t in that particular case. That is what we will be doing it, but for all these things this is what is the main thing that we will be using it. Okay. So, this ergodic theorem for this CTMC is what is the main backbone on which the models solutions are all obtained in for various queuing models. Okay. Fine, we will talk about that when we start this queuing model. So, we will end here. Thank you. Bye.